Hello.
Hello, sir. Hello,
Hello.
sir. Can you hear me?
Yes, sir. Yes, ma'am. Sorry.
Okay.
My voice is audible, ma'am, clearly?
Yeah. Your voice is audible, sir.
Okay, thank you, ma'am.
Sir, can you view me? Can you? Hello, Mallikarjun, sir.
Yeah, madam.
Yeah.
You are audible only.
Sir,
You
can you
can now
view me?
continue. Yeah, you can take.
Okay. Okay. Sir is ready, right? Sir is online.
Yeah, he is online.
Yes, yes,
Okay.
ma'am. I am.
Good morning, everyone.
Good morning, ma'am.
Good
Very
morning.
good morning, madam. Very good
Good
morning,
morning. Good morning, everyone. On behalf of VMTW, I, V. Susan Shalini, invite all the participants to join this webinar. Good morning, everyone.
Good morning, ma'am.
Good
Very
morning.
good morning, madam. Very good
Good
morning.
morning. With the support of the
everyone.
on behalf of VMTW, I, V. Susan Shalini, invite all the participants to join this webinar. All the participants to Good morning, everyone. And today's speaker, Dr.
Good
Rishi
morning, ma'am.
Kumar, Associate
Very good
Professor
morning, madam.
Physics,
Very good morning.
Head Department of Good morning, everyone. On behalf of VMTW, I, V. Susan Shalini, invite all the participants to join this webinar. Like sir has published international journals around 18 and national journals Dr. Rishi Kumar, Associate full paper. And there are many more important things about the today's guest. So, books, what Sir has been published is almost 3 books, and he has also done the editorial research advisory, and editorial members of Resources Scoopus Index journals, and reviewer of Science Director Elsevier and Springer, IOP, Willy, and RSC, Royal Society of Chemistry, and STM journals. So, the principals are our principals are Dr. G. Appara Naidu, and the HOD sir Dr. T. Srinivasulu, and the coordinator for today, Mr. A. Mallikarjun sir, and Mr. Satish K., an associate professor of chemistry. So, now it's a great honor for us to introduce today's resource person, Dr. Rishi Kumar sir, to lead the further presentation. And today's webinar topic is on liquid crystals and nanomaterial for display technology. Sir, dear honor to be you as a guest for today, sir. Hello, sir. Yes, sir. Yes, sir.
Thank you, ma'am.
Yes.
It's a very great opportunity for me to deliver the talk on liquid crystal and nanomaterial for display technology. And it is very great opportunity that I would like to thank college principal, organizers of the today's webinar, and all team for conducting this webinar on liquid crystal and nanomaterial for display technology. So these are the top outline of main top outline, and the main top outline of my talk is that for developing physics and application of nano particles top liquid crystal materials. For this, I will cover today what are the challenges in display technology, and what are the basics of liquid crystal and nanomaterials. As huge of audience have a lot of students, faculty members, and research scholars from different universities who is participating in this webinar. So I am trying to cover the basic of the liquid crystal and nanoparticles also in this webinar. So the main focus is on the controlling the issue of alignment and creating defect-free microstructures for improving the display devices. The focus on electrical tunable devices for the scope of industry interaction. So a lot of application in the field of liquid crystal displays. These I will be cover in the today's lecture. So can I start now? Hello, hello. I am audible.
Yeah, sir.
Okay, okay. Thank you. So from starting of this liquid crystal display learning, that was the innovation time in 1888 to 1899. The first Friedrich Riensel discovered the liquid crystal display, and in 1900 to 1917, the first display was discovered, that was crystal crystal display, and that display was the first discovered display in 1967. After that, the journey goes for developing the new liquid crystal materials, and the sharp main liquid crystal displays was discovered in the form of watches, and calculators was discovered by using liquid crystal devices. So that was in the year of 1972, in year 1980, when calculator and watches was discovered with the help of liquid crystal materials. And after that, new LCD color TV was discovered in 1985. That was the first LCD television, and displayed by TFT displays with the help of pneumatic indicator. So this was the display revolution. In starting, we have displays, this kind of displays. It is very bulky, and that is made of TF cathode ray tube. That was the basic electronics was used in that type of displays. After that, the display was formed by liquid crystals, and that was a laptop in laptop display where the liquid crystal was there. And after that, now we are in 2020, we are taking this type of in plane switching displays. Like in plane switching displays, we have the size is very small, because in starting we have bulky this type of displays, and now we have a flat displays. That displays are built by in-plane switching method, that is based on the liquid crystals, which are today's used in the display technology. And that displays are now introduced in the laptop, in television, in LEDs. So lot of LEDs have in-plane switching displays now. So the main this displays was made by Japanese and Korean and Taiwan companies. For example, LG, Samsung, these are the main companies which form this type of displays. Now, what are the major challenges for forming this type of displays? Because the electro-optic performance is the major is the major properties which are used in the liquid crystal display. For that, we have to control the liquid crystal defect-free film morphology, because these type of films are used in the displays, forming liquid crystals displays. And there is again another factor, that is surface anchoring condition, that I will show later, how this surface anchoring condition control the liquid crystals display performance. Then film thickness and viscosity is another issue for controlling the liquid crystal display performance, or we can say electro-optic performance. Now in these days, most of the displays in the mobile phone is also in plane switching based. So for that, for long running battery is required. For that, we all know that we need a long running mobile phone, and that is only possible when we have low threshold voltage there. And again, this is the property of material properties: switching response, tilt angle, spontaneous polarization. So all these material properties help to improving the liquid crystal display performance in electro-optics. Now, these are the main properties which we have worked out. On the basis of these properties, we can improve the performance of liquid crystal displays. But now, from the starting of basics of liquid crystals, I would like to introduce what are liquid crystals. So liquid crystals are basically the intermediate state between the crystal and the liquid. In crystal, there is a perfect ordering. That ordering calls a perfect orientational order as well as positional order. So it will show the crystal behavior. But in liquid, there is no positional order. Random orientation of these type of molecules are there. So there is no position order. But this liquid crystal material, which lies between the crystal and liquids, have possessed orientational order. They are arranged in some orientation, and there are some 1D and 2-dimensional positional order is also there, and they have fluid-like properties. So these are the definitions, how liquid crystal can be defined, how it can be distinct from the crystal and liquid material. So now I am going to the discuss there are two type of liquid crystals. One is based on the thermotropic, and the another one is based on the lyotropic. In case of thermotropic liquid crystals, the phase changes by changing the temperature of the system. The main phases of the liquid crystal changes as we change the temperature. But in case of lyotropic, if we vary the concentration of in this system, concentration of surfactant, then we get a different phases in case of lyotropic system. So uh, now I come to the unique property of liquid crystals. So unique properties are liquid crystals. They are pressure sensitive, temperature sensitive, and electric field. Sorry, hello. Kind of disturbance is there. So I'm audible now.
Yes, sir, you are audible. You
Hello.
are audible, sir.
Okay.
Yes, sir, you are audible.
Thank you, sir.
Share your
The
PPT, sir. Okay, sir. Okay, sir. Okay.
PPT is
Okay,
running.
okay.
The unique,
Wait, sir. Wait.
the unique property of liquid crystals are pressure, temperature, and electrical field. That means we can change the orientation of liquid crystals because they are pressure sensitive. If we apply some kind of pressure, there will be some changes in the orientation of liquid crystals. And if we change the temperature, we get different phase in different liquid crystals. That phase I will discuss in the later on the slide. And when we applied electric field, it these rod type molecules have orientation order, and they switch towards the direction of applied electric field. If we applying this side electric field, so these molecules have to rotate along this side. So this type of behavior is mainly responsible for the electro-optic characteristics of these liquid crystal materials. So now the next one is, these are the different phases of the liquid crystal. Like this phase is pneumatic phase. Here the orientation of liquid crystal materials are in this side some positional order is there, like in this in pneumatic chiral pneumatic phase have fingerprint texture, and this type of orientation is helical arrangement. All the molecules are arranged in the helical arrangement, so this type of arrangement is there, and this shows the chiral pneumatic phase, and this shows the schematic A phase, where only the positional order is there. That means all the rod-like molecules are arranged in a particular positions. In these form a layer type structure. So this type of texture, these textures are viewed under the polarizing optical microscopy, and these are the original texture of the samples. So all these phases are depends upon the temperature. Like some liquid crystal are shows pneumatic phase at room temperature. By raising the temperature, we get chiral pneumatic phase, then we get schematic A phase, then we get schematic C surface. So different phases are there. Now there are again surface alignment, some kind of surface alignment which plays the important role in the displays of liquid crystals. If the alignment is along this side, this alignment we can generate in the laboratory also, because these are very sensitive materials, and the alignment or we can this alignment we can generate with the help of some surface anchoring. So here this type of alignment is there. In first case, the alignment is in the all the molecules are aligned in a particular layer type structure. This will give planar alignment, and here is they are randomly distributed. There is no alignment, so we get focal conic texture here, and here is the fingerprint texture. So here we have created homotropic alignment, and according to the homotropic alignment, we get here a dark texture, or we can say dark state, because in these structures are viewed in the polarizing optical microscope, which have one analyzer and one polarizer at the 90-degree angle. So that means the light passing through the polarizer are blocked by the light passing through the analyzer. So that means we get no color or no response here, and we get black texture. This confirms that our alignment of the liquid crystals are homotropic in nature. So this texture is also named as homotropic texture. Next, we have some kind of liquid crystal, ferroelectric liquid crystal, which shows the schematic C star phase, and these phases are introduced by introducing some chirality. Chirality is because these layer molecules are arranged in a helical structure. This forms a helical structure, and this depends upon the tilt of these. The main response of these displays made by ferroelectric liquid crystals depends upon the flipping of this liquid crystal, rod shaped liquid crystal, or a switching of this type of liquid crystal. Like here I have shown, when we applied the electric field, these molecules are start rotating like this, and it forms a conical section. So the main switching depends upon the how much your this rod shaped molecules get response. So the response of the switching response of this rod-shaped molecule rotating along this side, and when we applying the field, this type of transmission behavior we get in the electro-optic behavior. So the transmission response is there. So this type in transmission response, or we can say electro-optic response, has been formed because these we can say they do not get switch off the field, and they have important properties. They show biostability, that they stable in both direction at the here as well as here at the saturation level. Saturation part is stable part of this type of liquid crystal displays, and it will show a wide angle response that is useful for the IPS displays. And the first discovered ferroelectric liquid crystal by the N.A. Clark in 1980. So these are the different response for the surface stabilized ferroelectric liquid crystal materials. Like here at the surface, some part in the texture is shown get stabilized by the and here is alignment, but this texture shows the stabilized texture, and there is again switching response at 0 volt. This type of behavior is there, but when we applied the field, so the whole the texture shows this, and this texture has been observed under the polarizer. So so also there is some doping of polymer in the liquid crystal to form polymer liquid crystal composites. In composite system, we have three categories: polymer stabilized liquid crystal, polymer dispersed liquid crystal, and we can form also some holographic by using these polymer dispersed liquid crystals. And then we have important part of this presentation, that is gas host liquid crystal, and where the gas is a nanoparticle, and the that nanoparticle how tunes the liquid crystals optics. This I will show in the next slide. And these are the some separation methods, polymerization induced phase separation method, that by using polymerization process we can induce the phase separation in the composite system, or by introduce some thermally we by changing the temperature we can induce the phase separation, or we can induce the phase separation by solvent method. So these are the setup in the labs which where we have studied the electro-optic properties of this liquid crystal system. This is the polarizing optical microscope, and this is the hot stage to measure the response with the temperature. So that hot stage is connected with this temperature controller. We control the temperature from this device, and we put the sample here. So by using these apparatus, we can measure the response with respect to changing the temperature of the liquid crystal, and we get different type of phases with respect to liquid crystal, and different type of phases respond to different type of display properties. So that means for pneumatic liquid crystals, I have shown earlier some textures, and that texture has been taken by using this type of setup. By changing the temperature, we get different type of response. And here we have a LCR meter. We can measure capacitance, and then by using that capacitance, we can find out the response or dielectric property response of this type of samples. So next, how the control of parameter that affects the liquid crystals with polymers. So polymer and liquid crystal composition is the major parameter. We can change the polymer and liquid crystal composite, and then we can form different type of liquid crystal material, composite materials, and get studies different type of electro-optic as well as dielectric properties. So all these parameters, viscosity, photoinitiator, matching and mismatching of polymer and liquid crystal during time, UV curing temperature, is used to study the liquid crystal composite material. So next, these are the hello. These are the respond of this type of material. From starting, we have this type of pneumatic material which have thread-like structure, and we doped with the polymer. Uh, and we take here in that case the 8 weight% of polymer. If we take 8 weight% of polymer and 92% of this type of liquid crystal, we get this type of texture that is green in nature. This is called polymer stabilized texture. After UV curing, after polymerization induced phase separation, this can be achieved, and this type of texture is used to create the different type of display material. So if we varies the polymer concentration 50 weight% and the 50 weight% is pneumatic liquid crystal, then we get this type of droplets, liquid crystal droplets, and that is the polymer dispersed pneumatic liquid crystal composite which forms, and this gives the different type of display behavior. By using that type of UV curable polymer, we can see here the different type of droplets are there. That these droplets behavior gives the different type of response in electro-optic properties. Then we added some type of dichoric dye to increase the contrast of this type of droplets. So we achieved some contrast in this type of droplets. Then we change the liquid crystal from pneumatic to ferroelectric liquid crystal, and we put the UV curable polymer here, and we get this type of droplet. That is again different type, different configuration of droplets which we have achieved here, and after that we put there chiral molecules, and we introduce the chirality in the textures. That chirality gives the twisted pneumatic liquid crystal displays, which will be helpful to create the twisted pneumatic liquid crystal displays. And again, this here is the texture of polymer stabilized ferroelectric liquid crystal. This shows magnetic C star phase, and this is the hypothetic model given in the paper of journal optical materials. This so basically what we are going to create a capacitor. So how we are going to create a capacitor, that I will show you on next. This is the capacitor, and these are two IDO substrates. This capacitor is made of two IDO substrates, and we put the polymer composite material which we have prepared in this capacitor, and then we see the response by applying the AC or DC voltage, and with respect to that voltage, the charge are induced, and here I have shown in at 0 voltage these droplets have no charge in the capacitor, but when we apply, these droplets get distorted. That means charge is responsible which distort the size, and there is again some kind of elastic constant which varies with the application of field there. So these are the preparation method for to prepare the liquid crystal displays. First of all, we check these displays are made by the ITO, and we check the glass substrate by using multimeter. We check the ITO of the glass substrate. Then we introduce alignment by using spin coating unit or polyamide layer on that substrate. After achieving the alignment on that substrate, we fill the samples. We fill the samples, and here is some spacer is there. We put the spacer on this substrate, and further we put the another substrate on this sample, and we clump the cell. This forms the capacitor like structure, and we put the sample here. That sample have flow like properties. That sample have flow like properties. So sample get filled in this substrate in this liquid crystal cells by heating it, and after cooling it we uh, again set we again investigate its morphological property by using the optical microscope, or by using the polarizing optical microscope. So these are the material used, which are used for the investigate liquid crystal properties. So here we have used ferroelectric liquid crystal material, which have tilt angle 25 degrees Celsius, spontaneous polarization 29 nanocoulomb per meter per centimeter square, and the switching response is 44 microsecond. Again, the pitch is 3 micrometer, and this sample shows different phases: magnetic C star phase at minus 30 degrees Celsius, magnetic A star phase at 62 degrees Celsius, and chiral magnetic phase is 76 degrees Celsius, and 86 degrees Celsius is isotropic phase. This phase sequence is given by this paper by Dr. A.M. Brother in Physical Review A, published in 1989. So this data has been taken from here, and sample is used for the further investigation. So this type of sample, ferroelectric sample, which shows magnetic phase star phase, have this type of zigzag defect. So that zigzag defects, which was further need to improve by applying some some basics of nanotechnology, or by adopting of nanomaterial, we have to need to improve the response of this sample. So this is the main target, that we want to increase the response of this ferroelectric liquid crystal displays, and we reduce the zigzag defect, and introduce enhance the electro-optical property. So this was the main reason to study the sample with the nanomaterial, because liquid crystal have some kind of chevron-like defect structures. That defect has been stabilized by some kind of nanomaterial. So this we need to this is suggested that nanomaterial can improve the ferroelectric liquid crystal matrix. So we choose different type of nanomaterial to disperse in the ferroelectric liquid crystal. So this is the switching response of liquid crystal displays with respect to voltage. Here I have applied 1 volt per micrometer, and the textures are showing different colors. This means the rod-like molecules, which are arranged in the helical pattern, shows different orientation. At 1 volt per micrometer we get different orientation, and 2 volt micrometer we get different orientation. Mean to say, the liquid crystal molecules are rotating like this way, and showing different response towards the wavelength. As the liquid crystal molecule get tilted, different wavelength can be achieved, and that is the main requirement to introduce the optical properties, or to introduce the to study the optical properties of this birefringence material. So now, what is the need to study the nano composite? Why we are studying this type of nano composite? So because we want higher color contrast, we want a cheaper device, faster device, because all of us have now IPS displays in the mobile, and then that gives the faster and cheaper response, and easy to fabricate. And the main advantage is the low voltage operatable condition. That means that device with the nanoparticles operates at very low voltage and consuming less power. This is the importance of the nanotechnology, why we club the nanotechnology. This is the way. Now I am going to explain some nano, what is nano, why we chose the nano, because some students are there. So yeah, some of them must be familiar to the nanotechnology, or some of them are not much familiar. So I will go to explain some basic of nanotechnology in 3 4 slides, so that you get response of or basics of nanomaterial, and then we implement. Then I will show how we implement in the these nanomaterial into the liquid crystal displays. So in nanoscale, what nanoscale is? The 1 to 100 nanometer particle is said to be the particle in the scale of nano. So if the particle size is greater than 100 nanometer, we can say 200, 300. That is not in the on the scale of nano. So that means only this range of particle having range 1 to 100 nanometer is said to be the particle of nanoscale. So different nano scales particle have been synthesized in today with the help of nanoscience. So nanoscience is the study of science behind the behavior and property of nanostructures, and the technology which are used for the fabrication and characterization of these nanostructure or nanomaterial, that will be implemented in the nanostructure device with the help of technology, and this will give a new technology that is called nanotechnology. So a lot of things I have shown how the nano scales varies. For example, if I am taking the starting from this is the 1 centimeter, that is equal to 10 raised to power minus 2 meter. But when I go beyond this at 1 millimeter, which is the minimum point on mark on the scale, if I see the scale, the first mark is of 1 millimeter. That means after going beyond to that 1 millimeter, we get 10 raised to power minus 6 meter, and that particle is not able to see with the naked eyes. So 10 mic even human eye resolution is 0.01 mm. Behind this 0.01 mm, we cannot see any particle with the naked eye. So for that, for visualizing that type of particle, we need some kind of microscope, special microscope, and a micron particle can be even seen with the help of simple microscope, because the best example is red blood cells, which will be useful, which will be visualized to the common microscope in the laboratories. Even in the testing laboratories, they have simple microscope. They used to measure the red blood cells, size of red blood cells, and after going beyond at the scale of 10 raised to power minus 9 meter, we have developed now lots of structure. This type of carbon nanotube, buckyball is there, nanotube electrodes are there. That needs that type of structure will be designed by well-defined equipment, and that can be visualize with the help of electron microscope. Either it will be scanning electron microscope or tunneling transmission electron microscope or some kind of atomic force microscope is there. So this, so dealing with the nano world, there is a lot of important equipment and infrastructure that needs to build at that nanoscale level. So variety of nanoparticle materials are there now. This is called nanorods, copper oxide nanotube, and even we can alter the shape like this CDT nano tetrapods are there, and we have worked on this type of material also. And single wall carbon nanotube. This is the transmission electron microscope. CAM micrograph of single wall carbon nanotube, and this is the uh, CAM micrograph of nanowires. Variety of nanomaterials are there. So how to choose that type of nanomaterial to work on the liquid crystals to improve the liquid crystals display behavior. So lot of properties have to study. Lot of properties have to need to optimize. So variety of nanoparticles are there and used in the textile, biomedical application, healthcare application, food agriculture, industrial application, electronics, environment, renewable energy, and textile application. Lot of applications are there. So this nanotechnology was discovered by Richard Feynman, and he states that there are plenty of room at the bottom. Uh, how there are plenty of room at the bottom, I have shown here at this slide, because this is our bulk material. So in case of bulk, there is no cut, and the number of operation, because without cut is this is without cut, so number of operation is 0, and the surface area of this bulb, this is a cube. So cube what is the surface area of cube? 6 a square, and volume is a cube. And we cut it from the center. It will divide it into two parts. One part is there and another part is there. So now the number of operation is 1, and the surface area changes with the journal formula. I am taking here 6 plus 2n into a square, that is 8 a square and a cube. Now I cut again two parts, one part from this side and one part from this side. Now the surface area is going to increase, but volume is remaining the constant, because when we add the volume of these four boxes, the volume remain constant, but the surface area is going to change. That is 10 a square. Again, I put here n is equal to 2. 6 plus 4, that means 10 a square. That means surface area is 10 a square. After that, I cut into four parts and getting the surface area 14 a square. So that means whenever we are cutting this block, that means surface area is going to increase every time, but volume remain constant. That means what is going to happen in the surface area to the volume ratio. So if I divide its surface area to the volume, the ratio, that is surface area to the volume ratio, increases with decrease is dimension. This is the main part. If I suppose this is your bulk material of the range of micrometer, and we cut it simply and it will become nanomaterial. In that case, surface to volume ratio increases with decrease in dimension. That means we get higher surface area to volume ratio, means that will gives you important property of the nanomaterial. When we see these nanomaterial into the bulk from the XRD, X-ray diffraction, and we say this is the bulk silicon nanoparticle and this is the nanosilicon particle. What is difference between the peaks? Peaks get broad in case of nanomaterial. But in case of bulk, there is no broadening here. So the width again it can be calculated by using of Debye-Scherrer formula in case of nanomaterial. So this is what I have already explained, that we are going to cut some material uh, into number of pieces until it will go to the nanoscale. So that means at nanoscale we form here nanoparticle. This approach is called top to down approach, whereas if we take small particle and we club make its cluster and it will introduce a nanoparticle, that approach is called bottom up approach. So that are two approach for the synthesis of nanomaterial. So now, quantum confinement is there. Some material shows a quantum confinement. For example, quantum dots where the all the three dimension has been confined. In nanorods, only two dimension has been confined, and in nanofilms, one dimensional has been confined, and two dimensional is free. Electron is free to move into the two dimensional. So in bulk all the three dimensional are free, so it is called three dimensional material. So I have worked on the quantum dots, this type of zero dimensional material. So what is going to happening by by using electron confinement? The density of state varies. The density of state varies with the energy of the particle. So this behavior describes the density of state, how density of state varies with the, and size of the material matters. Like in bulk, I am taking here example of gold. Gold is of yellow color, and uh, the material property do not change with the size. In case of bulk material, resistivity remains same, melting point remains same, optical absorption remains same. But when we change the size, different color has been achieved, because the with the size here I am showing, with the size here, this is the particle of 40 nanometer and the color is blue. 80 nanometer, the color is again changed. 120 nanometer, yellow color is there. At 50 nanometer, green color is there. 100 nanometer, here is there. So different particle is there with different size, and they will show different color, because the nanomaterial have a characteristic property of change in color, because it shows the characteristic energy band gap at the nanoscale. So now I am talking here what is the need of nanomaterial, why nanomaterial are embedded into liquid crystal for studying different properties. These are the main properties what we can study in the field of liquid crystal for fabrication of displays, like switching time, impedance, threshold, concentration of impurity ion, AC conductivity, anchoring effect, activation energy. These are some thermal parameters, and we can also uh, investigate memory effect with respect to temperature, or by changing its mechanical or thermal property. And the work has been done by choosing some particle like nickel oxide, silicon oxide, zirconia, titanium. A lot of particles are there. So these liquid crystal devices have their unique advantage, yet there are many obstacles to be removed, which have discussed earlier. And for the required purpose, we merge the liquid crystal with the nanotechnology. So this is the need why we this is the need of investigating these nanomaterial of liquid crystal to investigate their electrical property, thermal property, and memory effect, because the nano material get stabilize these liquid crystal microstructures. So this is the result which I am going to show. Silica nanoparticle. I have also worked on silica nanoparticle in liquid crystal, but I am taking here the example from this paper. Uh, that is, these are liquid crystal domains, and when you embed nanoparticle, doped nanoparticle into liquid crystal, nanoparticle have a segregation problem. So how it can be? We want a particle does not segregate. Particle does not segregate into the liquid crystal matrix. For that, we done the capping of some nanoparticles before the doping. So if we cap the nanoparticle with a proper, giving a proper hydrophilic or hydrophobic structures like this one, so we get a better response because there is no segregation in the liquid crystal matrix, and we get a improved transmittance in that case. So this I am showing a result of my own paper. These are the liquid crystals, only pneumatic liquid crystals, where no silica nanoparticle is there, and means this is the undoped sample. Only pneumatic liquid crystals and some polymers are there. After adding 1 weight percent, I got improved 1 weight percent of silica nanoparticle. I got improved these droplet structures. That structure can be investigated through polarizing optical microscopy, and when the concentration is to 2 weight percent, it gives a better contrast which will be applicable to the displays. And when we remove this liquid crystal from this cavity, only polymer structure left, and this structure was investigated through the uh, scanning electron microscopy, and these are the micrographs taken from the scanning electron microscopy to investigate these droplets, these polymer matrix structure. So here is some writing is here, and see the from this matrix to this matrix, the polymer matrix surface also can be modified with the help of nanotechnology. But when it the concentration reaches to the 3 weight percent, the molecules get silica nanoparticles get segregated with this polymer matrix, and here some segregation is there which decrease the contrast here. So that means we are getting here poor response. So at 3 weight percent. So we have studied this series, and the result has been published in Liquid Crystal Journal. So this is again the contrast, and this is the important parameter which have been studied, the refractive index. Refractive index also changes with the doping of nanoparticle that was investigated with the help of a base refractometer. And again the pore size here I have shown at lower magnification 1000x, and here I have shown 5000x. So this is the pore size taken from the scanning electron microscopy, and see here this is the micrograph of nano-doped liquid crystal. So we are getting here a symmetrical, near about symmetrical I can say at the micron level. In case of 1 weight percent silica nanoparticle is there, so we get here better contrast in that, and even we have measure the thickness of these materials. This is the interface with the substrate, and this is the film. And film I have studied, and by using the scanning electron microscope, its thickness is near about 18 micrometer. So we have also done fluorescence analysis of these films, and we apply different voltage to measure the photoluminescence contrast. So by varying the voltage from 0 volt to 4.8 volt here. This is the switching response of fluorescence intensity. So that means fluorescence intensity varies with increasing the voltage up to 48 volt. 48 volt I have studied from 0 volt to 48 volt, and near about 48 volt this distance is going to decrease, and we get a saturation behavior after the 48 volt. So I have studied only up to the 48 volt. So next, this result has been published, and we get better result in case of 1 weight%. Even we have tried to uh, investigate below 1 weight%, but in that case again we get better result of 1 weight% of silica nanoparticle. This is the switching response of voltage, switching response of liquid crystal film with respect to the voltage, and the result has been published in liquid crystal journal. So these type of films can be applied to smart window, or we can say switchable window. Here in off states, no voltage has been applied, so liquid crystal molecule are within droplet or within cavity. They they are in still position, but when we applied field, they trying to align in the direction of applied field, and even there is a refractive index factor is also play, elastic constant also plays great role here with the by changing the voltage, or these molecules get aligned perpendicular to the substrate, and the light passing through this window is get passed through, and we get here a clear image from this. But here the image is opaque because liquid crystal are in random direction, and the film may be of the order of some micron is there in between the two substrate of liquid crystal. So here we have applied some field, so get a transparent. So this means this type of optical shutter which we can construct with this liquid crystal displays. These are summarized, that nanoparticle is refractive index of the composite, and the optimize whether we are trying silica or some other nanoparticle. So some optimization of nanoparticle quantity is there, that we want to know which quantity of nanoparticle, which composition of nanoparticle gives the better result for the display, for the faster switching response and better contrast. So again, we have worked on the zero-dimensional quantum dot, that is TDSC quantum dot, and this is the TAM micrograph, and from this we get 6 to 7 nanometer range particle, and we dispersed into the chiral liquid crystal or chiromatic liquid crystal. The 0.02 weight% of quantum dot does not disturb the fibrous structure, and here it was disturbed because the concentration is at 0.06. Even the meanwhile concentration has been tried for this, but only we have here chosen the best concentration, and the worst concentration was which was is there. So that means that much concentration of quantum dots gives the better result, 0.02 weight%, and this result is also published in the, and we have done again polarized fluorescence spectra for this to measure the order parameter, and even here we have get better ordering, 0.4 is there, and here is least ordering, 0.03 here. So that result gives the same that gives the command to the this 0.06 also. So means there is some other studies which we can done to measure, and this is the electro-optic study by using fluorescence spectrophotometer. With the voltage we have applied the uh, liquid crystal cell and find the response, and we get here a minimum response that is near about 2.6 volt per micrometer at 0.02 weight% concentration of CDS in quantum dots, and this gives the uh, driving voltage for this is the undoped material is very less, and the agglomerated one, that one where the concentration is 0.068% is the we get the poor response here. So even the that response is very low from the undoped material. So that way this clearly shows that how nanoparticle or quantum dots affect the optical switching of the liquid crystal displays. So then we have studied the polarization response by using by connecting the cell with the oscilloscopes, and we get this type of hump here, which is responsible for the polarization, and then we have calculated the spontaneous polarization with respect to different temperature and find out the different behavior for the different phases. That is, in symmetric C star phase there is larger polarization, so it is the best to form liquid crystal display. Even the polarization are used to store the data device. Is we can implement this type of material where we need to store the memory. So this matrix C star phase is helpful to introduce or to build the memory device. But in case of symmetric A and N star, these are not able to build the memory device. And these pneumatic star, chiral pneumatic phase, even very good space to build the liquid crystal displays, or we can say electro-optic liquid crystal displays. But in memory devices, we can use ferroelectric liquid crystal display. Then we come to the tilt angle measurement. In tilt angle measurement, when we applied field to this type of molecules, it gets switches. It get tilted. This gives the low tilt and this gives the high tilt. This switching gives you the switching time. Means lower is the tilt, lower is the response time. Higher is the tilt angle, higher will be the response time. That means we in the liquid crystal displays we need lower tilt angle. That means lower switching response time is there, and in case of a higher tilt angle we get higher response time. So here I have studied a different response time for the different temperature, and the fall time increases as the tilt angle increases. This was concluded from these type of studies, and this gives the method how we can measure the response time. We have to measure the this distance of hump from this to this, and the distance of hump from this. See, in the doped sample, this distance is less and this distance is greater. That means we are able to decrease the response time in that case of doped sample. So even we have done dielectric measurement, but I'm not going to discuss here because of already there is a lot of time, and some polymer stabilized system is there, and that study was done with the by choosing polymer and ferroelectric liquid. This type of thread-like structure has been formed with the liquid dropping of polymer into the ferroelectric liquid. After stabilizing this work has been done with the help of dye, and in case of dye we get this type of fibril structure. And if